All right, find all the horizontal and vertical asymptotes of the graph of the function f of x is equal to 2x plus 3 times x minus 1 over x plus 2 times x minus 1. Use limits to explain your conclusions. Pause the video, give it a try, then continue the video to check your answer. All right, let's take a look at the solution. So first off, let's start with vertical asymptotes, because I think in some ways that's easier to look at. In this specific situation, if we think about what we learned once again in pre-calculus, we know that the vertical asymptotes will be where we have domain issues. And in this case, as a rational function, we're going to have issues at -2 and at 1. So using limits, we could say then that the limit as x approaches -2, say from the left of our function, is going to be the limit. Actually, let's go like this, is going to be equal to, if we were to take -2 and plug it into the function, it would be 2 times -2 plus 3, and then -2 minus 1 all over. And then this part right here will be -2 minus 1. But this part over here, and that'll cancel that, this part right here will be a -2, but from the left. So just slightly to the left of -2. So this will become out a really small negative. So using the logic we had before, this is a constant divided by a really small negative. So this becomes a really big negative. Okay? Now following that exact same logic, but from the right, in this case, we would get our constant, but this time divided by a really small positive, right? So we have our 2 -2 plus 3 over positive, which would then give us positive infinity. So we can see that there is definitely a vertical asymptote at x equals -2. Following the exact same calculus logic, we could show that the same thing was happening at +1. Now, as far as our horizontal asymptotes, remember those are achieved by looking at us approaching infinity. So I'm going to take this expression and rewrite it in the expanded form. So we have here 2x squared plus 2x minus 3 over x squared plus x minus 2. So same expression, just in a different form. Okay, now using what we learned before, we're going to rewrite this by dividing every term by that largest degree. So 2x squared over x squared, 2x over x squared, minus 3 over x squared over x squared, plus x over x squared, and then of course minus 2 over x squared. And then simplifying, this becomes the limit as x approaches infinity, 2 plus 2 over x minus 3 over x squared, 1 plus 1 over x minus 2 over x squared. And then every term that is over x goes to 0 per our theorem. And so we get 2 over 1 or 2. So we have a horizontal asymptote at y equals 2. Note the same thing would occur approaching negative infinity. All right, today's lesson's topic is continuity. We're going to say in calculus that a function f is considered continuous at a point A if the following conditions are met. F of A is defined, that is, A is in the domain of f. The limit of f of x exists as x approaches A, and the limit of f of x as x approaches A is f of A. That is, what it's defined at is the same as the limit. Let's take a look. Example 1. The graph of the function f is shown in the figure below. Use the graphs to determine whether the function is continuous at 1, 3, and 5. Now note, these three conditions must be met. It must be defined, the limit must exist, and they must be the same. Let's start with 1. At x equals 1, we see that the function is not defined. So we are going to say x equals 1 is, actually let's state that differently. We're going to say f of x is not continuous at x equals 1 because it is not defined, right? Did not meet the first condition. Okay, now what about at 3? Okay, so at 3, we see that it is in fact defined, but we have a problem. The limit from the left approaches -1, and from the right approaches 2. That means the limit doesn't exist. So f of x is not continuous at x equals 3 because the limit of f of x as x approaches 3 does not exist. And we could get a little deeper here and put a little note because the limit from the left and the right are not the same. All right, let's check our last point. Sorry. Okay, so let's check at 5. Okay, so at 5. Let's see, is it defined? Yes. Does the limit exist? Yes. Or are they the same? No. Okay, so f of x is not continuous at x equals 5 because the limit of f of x as x approaches 5, in this case is 1, is not equal to f of 5, which in this case is 3. All right, example 2. Determine whether each function is continuous at the given value. All right, so remember, 3 conditions. F of x has to be defined at the value, and the limit must exist, and they must be the same. Let's check the first condition, f of 2. Okay, we get 2 squared minus 2 over 2 minus 2. That is 0 over 0. It is not defined. So immediately at this point, we can see that we're going to have a problem, right? And this cannot be continuous, okay? So not continuous. Because it's undefined, right? Because f of 2 is undefined. All right, let's look at the next one. Okay, so let's check our first condition, g of 0. Okay, so it is 1 over x squared if we're not 0, and 1 if we're at 0. So this is defined as 1, and now let's check our limit. So the limit as x approaches 0 from the left is going to be the limit as x approaches 0 from the left of 1 over x squared, which is essentially 1 over really small negative squared, which is essentially 1 over a really small positive, which is infinity. Okay, now the limit of g of x as x approaches 0 from the right is the limit as x approaches 0 from the right of 1 over x squared, which is 1 over really small positive squared, which is 1 over a really small positive, which is infinity. So the limit exists, but the problem is the limit is not the same as what it's defined at. So we're going to say then that g of 0 does not equal the limit of g of x as x approaches 0. So g of x is not continuous at x equals 0. And I guess up here we should also say not continuous at x equals 2. Be really specific.